Bismillahirrahmanirrahim. Welcome to class of Irrigation Engineering for section A and D. Today is 1 hour class and it is 30th of March 2021. Today we are starting the new topic. It is regarding how to calculate water requirement for crops. How to calculate water requirement for crops and what is the necessity of doing it. Why we have to calculate crop water requirement. And the second part will tell me uh, the relationship between water in soil and its relationship with the plants. There is a particular quantity of water which we need to supply to soil if we want a good nourishment, if we want a good growth of crop, then a particular quantity or particular depth of water need to be applied to the soil for a particular crop. Then crop will be able to utilize it fully. If we apply more than that water, that will be wasted in deep percolation, or it will run away from that place to the drainage system. And if we apply less than that, crop will not be able to get the required quantity of water. So we need to understand how much is the good quantity of water for a certain soil, for a certain plant. So that will be informed to you. ये दो टॉपिक्स हैं और we will try to cover it in 1 hour or 2 hour maybe. Maybe it will extend to the next lecture also. So this crop water requirement, if word is easy requirement for a crop, and if we see its definition before going to its importance, then it's better that crop water requirement is the amount of water or quantity of water which is required by the crop in a given period of time for normal growth under field conditions. So it is simply the requirement, the water which we have to apply to the crop, or the water which is required by the crop, and it is related to a duration. So crop water requirement can be specified for a 1 day, crop water requirement can be specified for 10 days, and crop water requirement can be specified for the whole season or whole period of the nourishment of crop. So it has relationship with the duration for a certain duration, and it mentions the quantity. And quantity of the water applied to the crop or applied to the soil or applied to the field can be mentioned either in terms of volume, so much cubic meter, so much liters, so much acre feet of water should be applied, or it can be mentioned in terms of depth of water uh, for a unit area, or for a certain area, depth of water. So that can be converted into volume easily multiplying with the area on which that depth of water is being applied. So quantity of water or amount of the water which is required by the crop in a given period for its nourishment, for its growth under the field condition, under the condition in which crop is there. So that is called as crop water requirement, CWR, crop water requirement. Why we have to do it? Why we have to calculate it? Because the need of agriculture is already understood by you. We are reliant on agriculture, and agriculture in Pakistani environment, now you are familiar that agriculture in Pakistani environment is sustaining on most of the area, it is sustaining through irrigation. And irrigation, now is the artificial application of water. So if we are providing irrigation, and if we don't know what is the requirement by the crop which we are growing over there, then we will be not providing required amount of water. We will not be planning in a good way. We will be either supplying water in less quantity or more quantity. So both way are not acceptable. So for efficient planning, efficient irrigation, in general, we need to know what is the crop water requirement, and and we should know what are the methods to estimate it. And it also helps us to decide what should be the cropping pattern of the area. cropping pattern, as it is clear from the words cropping pattern of the crops in which the crops are sown in an area, crops are cultivated in an area. It does not mean some figure, some photograph. It does not mean that. So, cropping pattern mentions or describes the percentage of the area which is utilized for a certain crop. If we have total Pakistan area, if total irrigated area is, for example, 16 million hectare or 20 million hectare is the total irrigated area. So if I make a table that 30% area is under wheat, 20% area is under cultivation of other crop grams, 10% area is under maize cultivation, 20% have orchards, and so on. So if I describe the whole area which is under cultivation or under the any crop. So if I describe how much percentage of a certain crop is there, so that we say that description, that table, that data is called as a cropping pattern of the area. So it tells us how much area is under cultivation by a certain crop out of the total command area of a canal. So that should be clear. To decide this cropping pattern, we need to know the crop water requirement because this cropping pattern should match with the water availability. Some crops need more water, some crops need less water. So if I go to the income from a certain crop, then everybody will try to go towards a cash crop or those crops whose income is more. So then maybe we will not be able to provide sufficient quantity of water. So usually the farmers or the governments, they come up with a cropping pattern which suits with their climate and also which suits with the water availability. So if we know the crop water requirement and you are planning a new irrigation scheme like you are doing in the lab part, if you are planning a new irrigation scheme for a certain area, so size of the canal will depend upon water required by the crop. And the water required by the crop will depend which kind of crops you have agreed to grow over there. So which types of crop you are allowing people, you are allowing farmers to grow in the field. So that will be decided by the cropping pattern. So that cropping pattern, if you have to decide, then you need to know crop water requirement. Otherwise, you will not be fulfilling the requirements of the crops. Some of the students' mic is on, and who is he or she? I cannot see. So please make your setting in such a way that when you log in, when you join the team, your mic should be automatically off. Okay. So for deciding the cropping pattern, and you know what is cropping pattern, it is a description that how much area is under a certain crop in a canal command area. So for deciding how much area you want to put under under a certain crop and how much area under the other crop, how much area under the other crop, you need to know the cropping. You need to know the crop water requirement. That will also decide cropping pattern. If we know the crop water requirement for each crop, we can effectively use the available water. We can effectively use available water if we know water required by each crop. If we don't know water required by each crop, so then we will be giving water to the farmer at our wish, at our arbitrarily we will provide it to farmer. So that will not match with his requirement. Either we will be supplying more water or less water. So for effective use or efficient use of water, we need to know the crop water requirement. Also, we need to, for planning an irrigation scheme, as you are doing over here in lab also, if you are making a new irrigation scheme, like Punjab government is making a new irrigation scheme, they call it Jalalpur Canal system. So when they have planned that system, so they calculated first the requirement of the water for the crops they propose to grow over there. So from those requirements, they then decide the size of the canal, and then they are going to construct or design that canal according to that. So for efficient planning and design of an irrigation project, we need to know what are the crop water requirement, because that will be required to calculate the water requirement for an irrigation scheme. If we know the crop water requirement for each crop over there, then we multiply it with the area, then we can get the water required at the head of the canal. So that is also related to new schemes, and this effective use of water is related to existing schemes. So we can plan water resource development in an area. So that is similar to providing irrigation project or carry out the water resources development. Water resources development in making new infrastructures. So that is similar to the above point. Or if we want to provide reservoir, if we want to construct a barrage, so how much should be the size of the scheme? That also depends upon the requirements. And the requirements, agriculture requirements come from crop water requirements. So that is how it is related to each other. Irrigation requirement of an area. At the moment, how we are doing, we are supplying water to a farmland or to a field based upon water available in the canal, water diverted to the canal, and we fix a certain amount of time that this much time will be allocated to you depending upon the concept of Varabandi. There is a system of rotation of water availability to each farmer at each water course. So that is called as Varabandi, or a rotational system of application of water. So if that is considered as less efficient, that is a supply-based system. We have water, we will give it to them, even if they need it or they don't need it. But the alternate system is demand-based system. So demand-based system, the farmer asks, or the irrigation engineer or the scientists who are working over there, they see if what is the soil condition at the moment and how much water is required by the crop at this time of its growth period. So based upon the demand, if we apply water to the soil, to the crop, so that is called as demand-based water application or demand-based irrigation system. So that is considered as more efficient. If demand is there, we should supply water. If demand is not there, we should not supply water. So like we have the demand-based system in case of our water supply to the our houses. We open the tap when we need it, we close the tap when we don't need it. So, but that is not the case in case of irrigation. They have to utilize water whenever it is available. So, demand-based system, if we want to apply, so that is considered as more efficient. Then we should know how to calculate the water requirement currently. So, that is how it is related to better management or efficient irrigation system. Management of water supply from the sources. If we want to release certain quantity of water, at the moment we have at the moment we supply water to the canals, main canals, based upon their allocated water. Allocated water is historically whatever they were getting. So if system has the water available, if the river has the water available, we supply that much water which is allocated to that canal. We are not supplying water based upon the need of the area, need of the command area. So for better management of water supply, if we calculate crop water requirement first and then we supply water, that will be improving the system overall. So nowadays we have the methods available, latest methods available, in which on daily basis or on real time basis we can calculate the crop water requirement using either remote sensing system like satellites. They are looking at the crops. They are looking at the area. They can tell us the radiation coming out of that area, and from those radiation energy we can calculate how much is possible water requirement for that area currently. So based upon that, also we can see what is the stress condition of the soil, how much moisture is deficit in the soil. Also we can see what is the condition of nourishment of the crop, whether it is a well grown or well nourished crop or it is under stress. So based upon these indicators, which can be real time measured with the satellites or any system which is above the ground, or any system which is installed at the field itself. we can install tensometer in the field, and that can be linked to the laboratory, and we can calculate the moisture content directly sitting in the laboratory. So these systems are available. We are trying to move towards this system, which calculates the demand first, crop water requirement first, and then the system manager will decide to release the water. But that is at the moment at the research stage, still not being practiced at larger stage. So these are some of the reasons that we introduced to people for crop water, how to calculate crop water. Main thing is we want to efficiently use the water for agriculture, for irrigation, and that is only possible if we know the requirement of the crop in the field. Or if we want to plan the system, we need this crop. If we want to improve the efficiency of existing system, we need this crop water requirement. So that is the basic thing which we need. Like basic thing in concrete structure, you need to know the concrete strength. Basic thing in your building engineering is compressive strength of brick or steel or something like that. So similar is basic thing of our agriculture irrigation is how much is the crop water requirement. And there are easy way also available to calculate it, not very complicated. And there are more detailed, elaborate way also available to calculate it accurately. So three different methods will be introduced to you how to calculate crop water requirement. Okay, crop water requirement is in general total water required by the crop, and it includes a number of components that should be added to calculate the total crop water requirement. For example, crop water requirement consists of a factor or a component, we call it consumptive use. That utilization which is consumed by the plant or by the field itself. We don't get it back. So that is a consumptive use. It has been consumed. So crop water is sum of consumptive use, and it is sum of losses in the system, because actually we need to provide water in the field, but we have to calculate all the losses which we have to incur, which we have to suffer before that water reaches to the field itself. So in the canal system, we know heavy losses occurs 40%, 30%, 20% losses occur in the conveyance system. So that losses should also be added in the computation of crop water requirement. In addition, if we have certain special operation we want to carry out in the field, then that water should also be added in the crop water requirement. So crop water requirement includes consumptive use, it includes conveyance losses, it includes the special uses. So these three in combination is called as the crop water requirement. Either it will be measured in depth unit, or it can be measured in volume unit. Usually we measure it in depth unit, because it is then not specific to how much area we are applying to it. So if we mention the crop water requirement in depth unit, then volume should be calculated based upon local, how much area for which we want to calculate this crop water requirement. So it is usually mentioned in depth unit, millimeter, centimeter, or inches. So it includes this consumptive use is actually these two parts. One is called as evapotranspiration, and the second is the water used by the crops for metabolic growth. There is a minimum amount, less than 1% of the water is actually utilized biologically by the crop. Crop intakes water from its root, it moves through the stem to the leaves and then evaporate through the leaves. So that evaporation is called as transpiration. So while it is moving through the plant, a minimum quantity less than 1% or close to that percentage is utilized by the crop for biological actions, for metabolism. Rest is evaporated or transpired into air. So that is how we are differentiating over here. Water used by the crops for metabolic growth, and water which have been lost through evapotranspiration. It is combination of two words, evaporation and transpiration. because they are occurring most of the time together in combination. So they have carved out a new word, evapotranspiration. So that is one part. So that is sum up in consumptive use, evapotranspiration, and water use by metabolic growth. This component is so less metabolic growth that most of the time we only calculate evapotranspiration, and we say this is a consumptive use of the plant. Third thing is water conveyance loss, which is mentioned over here, and that depends upon size of the canal system. That depends upon canal wetted perimeter, how much is the perimeter or the width of the canal, because seepage occurs through the perimeter and evaporation occurs from the surface. So size of the canal do affect the seepage losses. It also depends upon the type of the lining carried out in a canal, whether it is concrete line or it is alluvial channel that we call as silted uh, uh, unlined channel that controls the seepage losses through the canal. And out of the total losses of conveyance, two are the major losses. One is seepage loss and one is the evaporation. Out of these, seepage is more quantity as compared to evaporation. If 100 is the total losses in the conveyance, 89, 90% is the seepage losses, 7, 8, 9, up to 10% are the evaporation losses through the canal. And third thing is the special application. Sometimes for preparation of the field, we need to apply extra water just once for preparation of the field. So there are sometimes when we apply water for the first time, we need extra quantity of water to soak the whole soil mass in a good way. So that water which we apply in addition to the normal crop water requirement, so that is the first application, that is called as core water, KOR, core water. So these are the special uses of the water. So for preparation of the land, we need sometimes water, so that should be added in addition to normal crop water requirement. Sometimes we want to remove the salts present on the soil, and we want to flush out the salts over there. So we apply the water in a speedy way, and salt present on the soil are dissolved in the water, and those are then drained away to the drainage system, or they percolate down to the deeper layers. So that is how we sometimes remedy or we rectify the salinity in a certain area. So that is called as salt leaching. If salt are present at the surface of the soil, so to clear that area or to reduce the salts, sometimes we carry out a heavy application of the water. So water then dissolve those salts, and in the dissolved form, either that water is released to the drainage system or it percolates down, and we get the better quality of soil over there. So this special need of the land, if it is there, that should also be part of crop water requirement. So mainly three components. One is consumptive use, and the consumptive use is comprises of evapotranspiration requirement and metabolic requirement, water required for metabolic growth of the crop. And second thing is the losses, conveyance losses in the system, because don't have the water present in the field, we have to convey it from far lying area. Sometimes we have to convey it for 100 of the kilometers. For example, you know this, you already know this Lahore branch is getting water from Marala, and Marala is 100 of kilometer away from here. So there are huge losses incurred in the conveyance system. So that should be added if we want to calculate the crop water requirement at the head of the canal system. If we want to calculate water requirement at the head of the field, then these conveyance losses will not be there. Then losses only occurring in the field will be considered, that we call as the field losses. So their losses are divided in this two way, conveyance losses and the field losses. So crop water requirement should contain all the losses which we expect to occur. So this graph gives you a taste of how much will be the crop water requirement or consumptive use by a certain crop. If you see the y-axis, so this is for 4 different crops, and these are related to somewhere in Canada and Alberta. So, but similar is condition over here also. Usually crop water requirement, when we calculate, it varies in millimeters or a part of inches on daily basis if we calculate it. So you see this is a fodder crop, alfalfa. Alfalfa local name, if you see on the web, you will see that this is crop which usually we grow in the field for our animals. In local language we call it berseem or lucerne, some people call it. So that is a normal fodder which we grow in our field. So for that, if you see the crop water requirement on daily basis, because when we define the crop water requirement, we can mention the crop water requirement for different period of time. Somebody can measure it for a 1 day. Somebody can add the crop water requirement for the whole crop period. So if I add a daily crop water requirement, it will give me the total crop water requirement. So that is usually called, if we add the crop water requirement for the whole base period, for whole the crop period, then another name is used for that. We call it delta of the water which is required by the crop. So variation, if I want to show you that it varies in millimeters, 1 to 9 millimeter. Ultimate requirement by alfalfa is 9 millimeter per day in Alberta area. And then immediately requirement reduces because this is fodder, and they cut it 2 or 3 times and it grows again. So the first cut have been done, the requirement reduces because the size of the crop reduces, so requirement reduces. So then it also grow again, its vegetative cover increases and its needs enhances and its requirement moves. So other crop which we usually see over here also, these corns or wheat crop, so they have the initially very less requirement. Then this is the growing period or development period. Then it has a maximum requirement when it is fully nourished, when it gains the full height, its leaves are fully grown, then its evapotranspiration requirement are maximum. Then it goes towards the ripening phase, and so that is the typical way of change of the crop water requirement during the growth period of the crop. Similar, you will see for most of the crop, only this peak requirement will change. Initially, they need less, finally. But if there are orchards, because they are multi-year crops, they don't start in a certain month. So initially they will have the similar, but for then a few years they will have the constant water requirements till the death of that orchard field, till we cut that orchards or gardens over there. So they can have multi-year water requirement. But usually our crops are a seasonal crop, 3-month crop, 4-month crop. Few crops are over the year. Few crops are extending for a year, like perennial crops, like sugarcane crop can be considered as perennial crop. So what are the factors which controls the crop water requirement? You can better understand the crop itself, the type of the crop. It controls the water requirement. If we say consumptive use is controlled by the crop itself, depending upon the height of the crop, depending upon the species of the crop, depending upon the leaf size, depending upon the stomatal opening in the leaves. The transpiration has to occur from the stomata. Stomata are the openings usually under the surface of the leaf on the bottom side. From there, water escape to the environment. So size of the stomata and its type of the crop, that controls its opening. So that controls the evapotranspiration. So one major factor is the crop type. So each crop has its own mechanism, its own biology. So it needs a requirement based upon its biological structure of the crop. So maize, sugarcane, we are using these names so that you should be familiar with these crops. Civil engineers are not usually familiar with the agriculture terminology, but because you are the provider of the water for this agriculture system, so you should be familiar with these names so that you can better discuss it with the agriculture extension people who are also working in the same area. So maize, sugarcane need more water as compared to the less water requiring crop like millet. Millet is the name for bajra. Locally we call it bajra. Sorghum is locally we call it jawar. So those who are from the village background, they are knowing about bajra and jawar. They should be remembering these names, millets and sorghum. And those who are from the city environment, maybe they are familiar with millet and sorghum. They should know their local names. So you should be knowing what we are talking about. So that's why I have written both the names. So second factor which affect the crop water requirement, of course, obvious is the climatic condition. Climate includes the temperature, climate includes the sunshine hours, climate includes wind, climate includes humidity. So these things control evaporation. So these things controls evapotranspiration. So these things control crop water requirement. It's because in hydrology we have told you evaporation from a certain area is dependent upon climatic conditions, and all these four things were informed to you. Hopefully you are familiar that evaporation is dependent upon energy available for evaporation. So energy available is through sunshine. Solar system is the prime supplier of energy for climatic system of this world. So is evaporation is a component of our hydrological cycle and our climatic system. Important component is evaporation. So evaporation is dependent upon sunshine, sunshine intensity, sunshine hours also, and the energy which is supplied for a unit area by the sun, that is constant in upper atmosphere. If we are in Pakistan and we go to the upper atmosphere above the local pollution, so above the atmosphere, the solar radiation is constant. But when it passes through the atmosphere, then some solar radiation is diverted back to the atmosphere, and some solar radiation reaches to the ground. So if we consider atmosphere effects are not there, for example, but it is there. If we consider that the same amount of energy is coming at a unit area, so then amount of energy absorbed by the soil is dependent upon the angle of inclination of that place with respect to the direction of the solar radiation. So sun is giving radiation, so ground, if it is perpendicular to that angle, it will gain maximum energy. But because solar radiation inclination changes from season to season at different location because earth is rotating, so location controls energy coming from the sun. In addition to the atmospheric condition, whether it is highly polluted or it is clean, in addition to the atmospheric condition, the local location also changes the amount of energy which is available for evapotranspiration. So that is why evapotranspiration at equator will be much different as compared to evapotranspiration from the polar area or from the middle latitudes. So sunshine is our sunshine energy is dependent upon location. It depends upon cloudiness. It depends upon atmosphere. So if it is more energy is available through sunshine, more crop water requirement will be there. So that's why we cannot calculate that water requirement for wheat is constant throughout the world. So it will be dependent upon the local climatic condition. It will be dependent upon the local energy available for evapotranspiration. Temperature is another way of measurement of energy. So if soil is up at higher temperature or if the plant is at higher temperature, its evaporation increases. So that's also controls the evapotranspiration. Humidity is indirectly proportional. More humidity reduces the evapotranspiration. If air contains more water vapors, then it is less evapotranspiration occur in that area as compared to an area where dryness is more, humidity is less, dryness is more, then easily water vapors can go into the air. So humidity is inversely proportional. Low humidity will give high crop water requirement. Wind speed gives a good mixing of humidity. So if high speed is blowing over there, high speed wind is blowing over there, we will be easily evapotranspiration process will be easier, and more windy condition will give rise to high water requirement. Water requirement change with the crop type, and the water requirement change with the crop age, growth stage of the crop. You can understand initially crop is very small, a small plant is grown, so it does not have much area for transpiration. It don't have much biological requirement also. So initially period only major requirement are evaporation. Transpiration changes with the growth of the crop, so that's why growth stage. And you have seen in the previous chart also in the previous that with the growth of the crop, the evapotranspiration requirement changes. Losses can be of different kind. Mainly we have the seepage or absorption losses and evaporation losses. And earthen channel losses due to seepage are much more than the losses due to evaporation. This message have already been conveyed to you. And these losses occur from conveyance losses we assume from start of the canal, that is from the barrage to the field outlet. Then we say that these are the field losses. After the outlet, we say some are the losses in the water course and some are the losses in the field. So they are excluding these conveyance losses. So they depend upon these seepage losses depend upon soil type. Clay soil will having less seepage, sandy silty soil will have more seepage. Subsoil water, a groundwater table, if there is groundwater table is higher, so then less seepage will occur. If groundwater table is close to the water level in the canal, if groundwater table is close to the water level in the canal or close to the bed of the canal, so then difference of the head, which will cause seepage, that will be less as compared to an area where groundwater table is too low, very low, then differential head or difference of head will be more, that will cause more seepage. So subsoil water level do affect the seepage quantity in a certain area. If all other conditions remain same, groundwater level do control. Age of the canal, usually new canal system, if it is unlined, new canal system have high seepage, and after running for a certain years, we expect that the small size silt or clay will slowly deposit at the bed and the side of the banks. And when these clay particles deposit on the bed and the side, then they give a kind of lining to the canal system, and the seepage losses reduces. So age of the canal, and this is oppositely also true if with the passage of the time canal maintenance is not carried out good, especially in case of lined canal. If its maintenance is not good, there are cracks in the lining, then with the age of the canal, seepage losses will increase. But if it is an unlined channel, usually we expect that there will be some deposition on the banks and the bed of the canal, and that deposition of the silt and clay, that will reduce the seepage losses. Position of the full supply level with respect to natural surface level. So that is one important factor which affect the seepage. If our canal is built on a fill material and natural land is lower, then seepage losses will be more in comparison to a canal which is made in cutting. From the natural surface level, we have cut the area and we have make a canal, that is called as canal in cutting. In comparison to that, we have to put a canal at higher bed, and we put soil over there, we compact it, and then we run the canal. So that is canal in filling. So if the canal bed is higher than the natural topography, more seepage is expected to occur, because we cannot compact the soil in a good way, and there are more chances of bank erosion and bank breakage, which will cause more seepage losses. Amount of the silt carried by the canal. Those canals which are carrying high silt laden water, they will cause low seepage, because this silt will ultimately deposit at the bed and the side of the canal, and then less seepage is expected. Those canals which have high wetted perimeter, those canals which have large area, cross-sectional area, or large wetted perimeter, will incur larger seepage as compared to a canal which have the same flow area, which have the same discharge, but it is running in a smaller section. Uh, Hopefully you understand, for a certain discharge we can make a larger section by reducing the velocity, and we can make a smaller section by increasing the velocity, and the velocity can reduce or increase based upon the slope. So if I want to convey 100 cubic meter of water, I can propose a smaller section, but then I need a larger velocity and larger slope. So same amount of water will go. Opposite is also true. I can put a larger section and smaller slope or smaller velocity. So that will cause more losses. If section is larger, so area from where seepage will occur, that will be larger. Perimeter is larger, so seepage will be more. So that you should also understand, that seepage losses are affected. So mainly it is the soil. Rest are most of the time are not under our control. Soil type, if it is sandy soil, huge losses will be there. If it is clay soil, less losses will be there. If it is lined canal, so these are some of the factors which affect the losses. In this figure, some of the losses are shown in irrigation canal. The left side figure is a canal. Losses are shown in a pictorial view. Evaporation losses occur from the surface. Percolation or seepage losses occur from the perimeter. Sometimes bank erosion occur and losses occur. Sometimes there are rats or some other reptiles or other animals, small animal, that like to stay in a cool and wet environment. They make their holes or they make their houses inside the banks, and sometimes they damage the bank totally, and piping occur through the bank, and that causes the losses. Sometimes water is released to the drainage system, so that is considered of losses. So these are some of the losses shown through the pictorial view in the canal system. When water reaches to the field, so here is the canal system, here is the, let us say, water course, it gives water to the field. So within the field there are mainly two kind of water losses. One is the deep percolation. We want that only the root zone should be wetted. If any water goes beyond the root zone, underneath the soil, beyond the root zone, that we consider as a loss. Sometimes we apply a high quantity of water and it overflow the bank of the field, and goes to the other field, or it goes to the drainage system. So that is also considered as the loss. So deep percolation and surface runoff can be considered as the losses. This evaporation and transpiration is considered as a requirement of the crop. We cannot provide water without this evaporation. This evaporation is also being reduced in the high efficiency system. For example, in drip irrigation system, we provide water only to the close to the stem of the plant. Close to the stem we provide water. So rest of the area is dry, so we get less evaporation in that system. So if you want to calculate the losses, here are some formula which will be required by you. Most of the canal system in Pakistan, unlined canals, have been designed by calculating the absorption losses using this Lacey formula. This is an FPS system. It says that absorption losses are 0.0133 times length of the canal in thousand of the feet into discharge of the canal in cubic power 0.5625. So this empirical formula, totally empirical formula, has been developed by Lacey, working in this area, and after observation from head to the tail, so much water was released at the head, so much water reaches to the end of the canal, and if there is no offtake from the canal, then the difference will be the losses. So losses are measured in a systematic way, of measuring the discharge at one place in the canal, measuring the discharge at the other place in the canal, and we stop any outtake from any outlet. So if there is no outflow from the canal, then only the difference will be because of the evaporation and the seepage. So using those data, this formula have been developed and have been utilized in most of the canal planning system, and you can use this formula also for conveyance losses calculation in the lab part 0.013. It is an FPS system. Keep in mind the units. Absorption losses will come in Q6. Discharge of the canal should be in Q6. This length of the canal should be converted into thousands of feet. For example, if the canal is of 5,000 feet length, then it should be L should be 5. So in this way, you can calculate that absorption. Another formula which is available in the literature given by Muffe, that reference is given over here. So they say that losses per million square feet of the wetted parameter. So K is loss in Q6 per million square feet of the wetted perimeter. What does it mean? For example, you want to calculate loss in a kilometer length of or in a mile length of canal. So this mile length of the canal multiplied by the wetted perimeter. So 1 mile is about 5,000 feet or 5280 feet. So that feet multiplied by the wetted perimeter. So that will be the area of the wetted perimeter, seepage area through the wetted perimeter. So if it is a million square feet of the wetted perimeter, so then this will be the K per million square feet of the wetted perimeter. Q is the discharge of the canal. So a canal, if it has 500 cubic of the discharge, its power 0.06 multiplied by 5 will give you absorption losses per million square feet of the wetted parameter. So depending upon how much is your million square feet of the wetted parameter, you can calculate the total losses in the canal system. So this gives you losses in Q6 for a certain length of the canal, and this gives you losses per million square feet of the wetted parameter. Either way, you can calculate it. In SI system, you will find some formula given in the book of S.K. Garg, Santosh Kumar Garg. He mentioned this for Indian area, but in the eastern side of Pakistan, especially Punjab, they have a similar condition as the western part of India, like Uttar Pradesh and Indian Punjab. So they are successfully using this formula in SI system. So seepage losses are 1.9 times Q power 1 over 6, and loss over here is in cubics per million square meter of the wetted parameter. So this formula is equivalent to this formula this is FPS system. This one is in SI system, 1.9 Q power 1 over 6. If we want to measure the loss using only the perimeter, not the discharge, that is also a good way of representing the loss, because more the seepage, more the area of the canal from where seepage can occur, more will be the seepage losses. So they are only using the width of the canal and the depth of the canal, and they have related it with the losses. So cubics of loss per kilometer length will be 0.005 B plus D power 2 by 3. They are using it in. So all these formula are for unlined canal. Usually we say that seepage losses are close to zero in case of the lined canals. So 857 is there. I take the attendance and we continue from here. Remember that this is slide number 10. If you have any questions, you are welcome. So that is the start of our this class. Maybe next time 3 methods will be informed to you. How to calculate the crop water requirement or evapotranspiration requirement. Any questions? I have taken the attendance. I will put it on the.
Excuse me, sir.
जी बोलो.
सर आपने दो सिस्टम बताए थे कि एक डिमांड बेस्ड सिस्टम है और एक दूसरा
लाइक बेस्ड सिस्टम. एक डिमांड बेस्ड, एक सप्लाई बेस्ड। आगे
कौन सा था सर?
तुम्हारी आवाज कट रही है, तुम्हारी आवाज कटी है, मुझे सवाल के समझ नहीं आई। कौन स्टूडेंट था ये, क्या नाम था?
रोल नंबर 48 एहसान।
48 तुम्हारे अब है, कनेक्शन है कि नहीं है? सवाल मुझे नहीं समझ आया। एनीबॉडी गॉट द क्वेश्चन? रिपीट कर दे।
यस सर, समझ आ गया मुझे। एक मैं सिस्टम के बारे में पूछा था, एक डिमांड बेस्ड सिस्टम आपने बताया था और एक सप्लाई बेस्ड सिस्टम, तो यही पूछना था।
सिर्फ नाम पूछना था। हमारे यहाँ पे जो है ना
Yes,
सप्लाई सिस्टम चल रहा है। हमारे पास अगर सप्लाई मौजूद होती है हम दे देते हैं, वी डोंट कंसीडर। लेकिन जब हम प्लानिंग कर रहे होते हैं, व्हेन वी हैव प्लान दिस सिस्टम, जैसे आप अपनी प्लानिंग कर रहे हो, तो उस वक्त आप डिमांड कैलकुलेट करके अपना सिस्टम डिजाइन करते हो। जब आप अपने कैनाल डिजाइन कर रहे हो तो आप फील्ड से चलोगे। फील्ड में ये क्रॉप है, क्रॉप को इतना पानी चाहिए, एक आउटलेट पे सारे आउटलेट का ये पानी इकट्ठा किया, इतना कन्वेंस लॉसेस है तो कैनाल का ये साइज होगा। तो प्लानिंग हम डिमांड बेस पे करते हैं, लेकिन हम सप्लाई जो है अवेलेबिलिटी या जो एक्चुअली प्रोवाइड करते हैं वो सप्लाई बेस पे करते हैं। लेकिन अल्टीमेट हम चाहते यही है कि हम डिमांड बेस पे जाएं ताकि पानी वेस्ट ना हो। सप्लाई बेस्ड सिस्टम में कई दफ़ा वेस्ट हो जाता है पानी। देयर इज रेनफॉल इन द सिस्टम एंड वी आर सप्लाइंग वाटर। तो वो उसको अवॉइड करने के लिए आवर विश इज कि हम उस तरफ जाएं, लेकिन इसके लिए हमें इंफ्रास्ट्रक्चर को चेंज करना पड़ेगा। वी नीड कंट्रोल एट ईच फील्ड। देन अभी हमारे गेट्स फील्ड के ऊपर मौजूद नहीं है, आउटलेट पे भी गेट्स नहीं होते। पानी होता है कैनाल में तो वाटर कोर्स में चला जाता है। So we need to change the system then. Okay, so I have taken the attendance. किसी और का सवाल है? किसी और का सवाल है तो वेलकम। तो ये कॉपी किया और पेस्ट कर दिया। Okay, you are free if anybody want to go.
Okay sir, Allah Hafiz.
कॉपी पेस्ट ही करना पड़ेगा, मैं भी भूल जाता हूँ। So CR, please mark the attendance, section A and D, and thank you and Allah Hafiz. I stop the recording and then I